Now we combine 22.15.2 and 22.15.3 by plugging this guy into here. We get the absolute value of r of x times log of x squared is bounded by twice of this integral plus big O of x times log of x. Our next job is to simplify the right-hand side by introducing a new function. This function will be denoted by v. This v will be the same v as in our plan of the proof of prime number theorem, introduced at the beginning. This guy is defined as r of e to the cos divided by e to the cos, which, if you read back to the original definition, is psi of e to the cos divided by e to the cos minus 1. Or if you want to write one step further, because psi was defined as the sum of lambdas. This is the sum for n less than or equal to e to the summation of lambda of n. And now let us plug this new definition back to here and use a changer variable. We'll do the following substitutions. We'll take x equal to e to the cos and t equal to x times e to the negative eta, which, if you plug x equal to e to the cos to here, this is e to the cos minus eta. How is this substitution reflected in the integral? For the limit, when t goes from 1 to x, eta will go from cos to 0. Because when t is equal to 1, that happens when eta is equal to cos. When t is equal to x, that happens when eta is equal to 0. Now with these substitutions, the integral will become, so the limits will be from cos to 0. From here, x divided by t will be e to the positive eta. And log of t, if you take the log of both sides, will be cos minus eta. dt will be x times d e to the negative eta, which is x e to the negative eta d eta, but there's a negative sign in the front. And now we reorganize them. By our new notation, this ratio is precisely v of eta. So this is the integral we obtained. And now we perform the following trick. We replace this cos minus eta by an integral. The integral from eta to cos of the constant function 1 d. Now let's introduce a new variable, zeta. This transform this integral into a double integral. And the integrand is a function that only depends on variable eta. And as a natural next step, we're going to use the Fubini theorem here to swap d psi and d eta, namely to change the order of integration. When you swap them, the integral we'll get is, to explain this part, we can draw a picture. Our domain of integration is this triangle, and I mark psi here. In the inner integral of the first double integral, this zeta moves from eta to psi. And in the outer integral, this eta moves from 0 to psi. But when you swap them, this eta will first go from 0 to zeta. And the variable zeta in the outer integral goes from 0 to psi. So this is how the Fubini theorem applied in this setting. Now let's continue. Remember, this x, by our substitution, is actually e to the psi. So we write it back. With this, we finish the change variable for this integration. And the left-hand side is actually easier. If you make the substitute x equal to e to the psi, then left-hand side, which is the absolute value of r of x times log of x squared, is equal to absolute value of r of e to the psi times psi squared. Therefore, this inequality becomes so that the remainder term, big O of x times log of x, upon this substitution, it will be big O of e to the psi times psi. And now we divide both sides by e to the psi. And know that r of e to the psi divided by e to the psi is v of psi. So we get the following integral inequality and call it 22.15.9. Now, from the definition of v, together with theorem for 14, this thing is actually bounded, namely big O of 1. Now we put alpha with the lim sup of the absolute value of v of c as c goes to infinity. Then this number is a finite number. And if we put beta to be the average and take the lim sup as c goes to infinity, but the mean value theorem for integrals is also bounded. But the definition for lim sup, we must have the absolute value of with eta bounded by alpha times some little of 1, where this little of 1 means a quantity that goes to 0 as psi goes to infinity. And this integral from 0 to psi of v of eta d eta will be bounded by beta times psi plus little o of psi. We have these two relations simply by the definition for lim sup. Now, if we plug this back to here, and note that this zeta will play the role of psi here. If you plug this back to here, we will get the absolute value of v of psi times psi squared less than or equal to twice the integral from 0 to psi, and the inner thing will be replaced by beta times zeta plus little of zeta d zeta, which upon integration is beta times psi squared, because the antiderivative of psi is psi squared divided by 2. So together you get beta times psi squared. And the remainder is little of psi squared as psi goes to infinity. So if you divide both sides by psi squared, v of psi absolute value will be bounded by beta plus little of 1. Now take lim sup as psi goes to infinity. The left-hand side will become alpha. Our alpha is this lim sup. So alpha is less than or equal to beta. This means the lim sup of the absolute value of this v of psi is always less than or equal to the lim sup of its average. Later, we will show that if alpha, remember, to prove the prime number theorem, it suffices to show that alpha is equal to 0. Alpha, namely lim sup here, is equal to 0. Then we are done, because then we will show that psi of x is similar to x. That is equivalent to the prime number theorem. Once we show alpha equal to 0, we are done. Later, we're going to assume by contradiction that alpha is not 0, namely alpha is bigger than 0. And we will conclude that alpha is bigger than beta, contradicting to this conclusion here. That is the plan to finish the proof of the prime number theorem.